In this video, we're going to handle simple sprite sheet animation in a pure Unity ECS game. This is one of the simplest forms of animation, and it can be done extremely fast so you can easily render thousands of units. Let's begin. Hello and welcome, I'm your Code Monkey, and this channel is all about helping you learn how to make your own games with in-depth tutorials made by a professional indie game developer. So if you find the video helpful, consider subscribing. So the new dot stack is wonderful and works insanely fast, but one of the biggest challenges is animation. As of right now, there's no implementation for the default Unity animations, so you have to build your own system. However, you need to be careful to make sure your animation system doesn't become a performance bottleneck. Now, one approach you can do is a mesh-based system. That is what I normally use in my videos, where each unit has a mesh and just modifies that mesh per animation frame. That's the approach I took in the Marines vs. Zombies video. In that scene, each animation frame is a different mesh, and the system just grabs the mesh that matches the current animation frame. That is a great approach, but also has some limitations, and it's quite complex to handle lots of different meshes. So here we're going to create the simplest form of animation, just some basic sprite sheet animation. So let's begin by writing some code. Let's start off by making a script to run our code, so a new C# script. Let's call it the game handler. Make a game object, and just drag the script. Okay, so let's start off by just spawning a simple entity and drawing it. Now, first of all, if you have absolutely no idea how ECS works, then check out the Getting Started video. That video should teach you the core of how ECS works and how to make an entity and add components. In here, I'm just going to quickly write the code to spawn our entity. So here, first we create a entity archetype. So here we just create it very simple with the translation component. Alright, so that's our basic archetype. Now let's create it. Alright, that's it, very simple. Let's see if our entity is indeed being created. So here we are, and here the entity debugger, and indeed we have an entity with a translation. Okay, good. Now let's see how we can draw a sprite. So let's make a system that will be responsible for drawing it. So let's put it in a different script, and let's call this the Sprite Sheet renderer. In here, this will be a component system. And now in here, let's just cycle through all the entities with the translation component. So we do entities for each. We grab a reference to translation component. And here we're going to use graphics.drawMesh in order to draw them onto the screen. Now in here you can see the parameters that we require. So essentially we need a mesh and a material. So let's add those as fields on the game handler. Now I'm only adding them in here just for testing. If you were to use this in a complete game, you would obviously place all of these assets in a more appropriate place. But for now, this is great for testing. Let's go into the editor. And here on the game handler, we can use, for the quad mesh, we can use the default quad. And for the walking sprite sheet material, let's create a new material in here. Okay, so we have our material. Let's drag our reference. Okay. And now here, back in our code, we need to access these fields from our sprite sheet renderer. So again, in this case, let's make a static instance that we can access. So we have a static instance that we set on awake, and then a function to get the instance, and through this instance we'll be able to access these fields. Again, if you were using this code in a proper game, you would manage your references in a better way. We're just doing it this way just for testing. So we can now go into the sprite sheet renderer, we draw the mesh, then we use the quad mesh. For the position we use the translation.value. For the quaternion we don't want any rotation, so quaternion.identity. And for the material, we use that material. Alright, so here is our nice function call. We're using the graphics API in order to draw a mesh, so we're going to draw a simple quad using our material. So let's see if it works. And yep, here we are, and there's our sprite sheet being correctly displayed. Alright, so we have the basics for drawing a sprite with a custom system. Now, obviously, the sprite is meant to only display one frame of the sprite sheet and not the whole thing, so let's see how we can do that. Now, the way we're going to do is by using a custom shader and passing a specific parameter to that shader. The shader will then use that parameter in order to display only a single animation frame. That way, every single unit will have the same mesh, the same material, but different parameters. So let's see the shader code. Here is the shader code. It is slightly modified in order to support GPU instancing, essentially so we can pass in different values whilst having the same mesh and material. Now, I must say, I am not an expert in shaders. This shader code here is put together from several examples that I found online. So if you see something in this shader that could be done better, please let me know in the comments. But the shader does work for what we're trying to do. Now, the key elements are down here. This is what defines what properties we can modify. So you can see that we are receiving an instance color and an instance UV. And down here we can access the instance properties. So we're going to pass in the main text UV as an array of UV coordinates. Each unit will calculate its own coordinates, and then the whole thing is drawn in a single draw call. Okay, so this is the shader. Now let's see how we can pass in these values to this shader. So here we have our draw mesh code. Now in here we're going to swap two things. First, we're going to pass values to the shader using a material property block. This is what actually contains the data that we wish to send to the shader. So in here we can do set the vector array. The name ID is the name that we gave in the shader. So here we are, it's the main text UV. Then we pass in an array of values. Now in here, this vector 4 is going to be the UV coordinates. So let's define it up here to see how it's set up. Essentially we have a width, a height, a X offset, and a Y offset. Now these are all normalized values, so regardless of texture size, the values go from 0 to 1. And with these values, we're essentially going to display the entire texture. So we have the offsets both at 0, so we're going to start drawing on the lower left corner. And the width and height is 1, so the entire texture, so we're going to draw the whole thing. So we create a new vector 4, and we pass in first the width, then the height, and so on. Then in here, we pass in this UV into our material property block. Alright, so that's our material setup. Now let's pass it into our draw mesh call. So here is the version of the function that we want. So first our mesh, okay, then the position, then the rotation, then the material, then the layer, then we need a camera, submesh, and properties. So for the camera, let's pass in camera.main. For the submesh, we don't have a submesh, so we'll pass in 0, and then finally our material property block. Alright, so just like that, we have our code to pass in custom values into our shader. So let's see. Now before we test, we need to assign our correct shader. So here in the material, let's go down into our custom and use the instance shader. Alright, now let's test. And yep, here we are. Indeed, we can still see our nice sprite sheet, and we can see the entire sprite sheet. Now let's make sure it's working by sending the UV for a single frame. So let's go back. Now here, in order to display just a single frame, essentially we need to mess around with the width and the offset. So in this case, we have 4 frames of animation, so what we do is 1 divided by 4. That way we have the width of a single frame of animation. So this is all it takes. Now let's test. And yep, there's our first frame of animation. Now let's test the second frame. So in order to have the second frame, we have the same width, but we modify the UV offset. Essentially, we modify it by the UV width multiplied by, in this case, by 1. And yep, there it is, our entity displaying the second frame of animation. Alright, awesome. So we can now play around with the values we put in the material property block in order to display different frames. In order to have sprite sheet animation, all we really need is to change those UV values over time. So let's handle that now. We're going to do all our animation timing in ECS. Let's make a new script and call this the Sprite Sheet animation. And now in here we're going to have two things. We're going to have a component to hold all of the animation data and a system to animate that data. So first start off with this simple component. So a component will be a public struct. Let's call this the Sprite Sheet animation data. And we obviously implement iComponent data. So this component will handle all the data that the animation system will require. So in this case, the first thing we need is the current frame. So we store a public int for the current frame. Then we need to know the total frame count. So a public int for the frame count. This will be how many frames total the animation has. Then we also need to know the time spent in this current frame, so a public float for the frame timer. And finally, a timer max to know when to go to the next frame. So again, a public float for the frame timer max. So as the frame timer increases, when it goes past the timer max, we increase the current frame, and as the current frame goes past the frame count, it resets back to 0. Alright, so this is all the data we need for a very simple animation. Now let's add this component into our animation archetype. So here we are, so we add with translation and a type of animation data. Now let's also set up our starting values. So here we are setting our component data. For the translation, let's start them off at 0, 0. And for the data, we start off at the current frame 0. We have a total of 4 frames of animation. The frame timer starts at 0 and frame timer max of 0.1. So essentially we're going to play this animation 10 frames per second. Alright, so we have our component data all set up. Now we need to make a system to actually animate. So let's go back into our script and down here, make a public class. This will be the Sprite Sheet animation animate. And will be a job component system. Now in here, we're going to create a very simple job. We want a job looping through all the entities with our animation data component. So first a public struct for our job, and will be an iJob for each with the Sprite Sheet animation data. Okay, so here we are cycling through all of our entities with animation data. Now in here we go into the data in order to access the frame timer and increase it by delta time. Now again, in a job we cannot use time.delta time directly, so we need to store it out here. Okay, so we increase the frame timer by the delta time. Then we need to test if the frame timer is past the frame timer max. So while we are above the frame timer max, we reduce the frame timer by the frame timer max, and we increase the current frame. So we increase the current frame and we get the remainder of the frame count. So as we go past the frame count, we'll loop back into 0. Alright, so that's it. Right here we have a very simple animation system that just deals with this simple data. So now let's schedule our job. And all we really need is to pass in the delta time. Alright, so that's it. And now in here we can also add a very simple burst compile in order to make it quite a bit faster. Okay, so let's see this job in action. Okay, here we are, and nothing moves since we aren't updating it yet. But if we go and inspect our entity, there it is. You can see the frame timer increasing with the delta time, and as it goes past the frame timer max, which is 0.1, you can see the current frame constantly increasing. Alright, so we have our animation data correctly working. Now let's calculate the UV frame based on that data. So let's go into the renderer system. And in here, the first thing we need to do is to make sure that our renderer only runs after the animation system. So for that, we can use the update after, pass in the type of Sprite Sheet animation system. That way this system only runs after the animate has done its thing. And now here on the entities for each, we grab translation, then also grab the animation data. And then in here, let's calculate the UV based on the animation data. So for the width, we have 1 divided by the total number of frames. So we can do dot frame count. The height, our sprite sheet is set up only horizontally, so we'll leave it at 1. And for the X offset, it will essentially be the width multiplied by the sprite sheet animation data dot current frame. So as the current frame increases, we shift what we show to the right. Alright, so that's it. Let's test. And yep, there it is. We have our nice entity with a very nice simple sprite sheet animation. Awesome. You can check the stats to see that we only have 1 quad, so 2 triangles, 4 vertices, and here's our nice unit. Alright, so now that we have the core working, let's see how we can improve upon it. Now, one of the things we can improve quite easily is regarding this UV calculation. So right now we're doing it here inside a for each, meaning we're doing it on the main thread sequentially for each unit. So a much better approach is to simply calculate this whilst we are calculating the animation, so right here. This way we're going to benefit from multi-threading as we calculate our UV. So let's simply add another field to our animation data. So in here a public vector for our UV. And here in our job code, after we modify the current frame, let's also calculate the UV. So let's copy this code from here into here. And we simply set the sprite sheet animation data.uv. Now in here, this could be further improved by caching the width and height and everything that doesn't change. But for now, this won't work and it will already be insanely fast. So now we are calculating the UV inside our job, so we can go back into our renderer system. And in here, we grab the UV directly from the sprite sheet data. Also another piece of data that we can calculate inside our job. In here, if we check out the draw mesh, you can see that there are several versions that work with a matrix. We're going to need matrices later on when we use the instance method, so let's deal with calculating that right now. Let's go into our animation data, and up here, we also store a public matrix for our matrix. So here, let's calculate the matrix. So for that, we go into the sprite sheet animation data.matrix, and we calculate it using this static function to get the translation, rotation, and scale. So we need the position, so that means we need to go up here in order to add the translation component to this job. Now in here, we just need to pass in the translation.value, quaternion.identity, since we don't have rotation, and vector3.1 for our scale. Alright, so this we have our matrix being calculated inside of this job, which is running nice multi-threaded code. Now just one last thing we need to do in order to handle sprite sorting order. It's in here, let's simply calculate a float3 for our position. So first we grab the normal position, then we offset the position.z by the position.y multiplied by a small value. And then this position is what we use in there. So essentially we're offsetting it on the z based on the y. This way we get automatic sprite sorting order. So sprites with a lower y will be in front of sprites with a higher y. So that's it for calculating in here. Now we can go back into our renderer system, and here we can now use the draw mesh function that contains both the UV and the matrix. Alright, that should do it. So essentially here on our renderer system, all we're doing is rendering our mesh. So all the work in terms of calculating the UV, doing the animation or calculating the matrix, all of that is done in a nice multi-thread code in here before that happens. Okay, so let's run the code and see. And yep, awesome, here we have our entity very nicely animated. Now let's change our code to spawn thousands of entities. So here let's create that. So here we have the code spawning 1,000 entities. Let's randomize their position and their starting animation so we can see the difference. Alright, so here we have a bunch of randomness so we can easily see everything. And let's test. And yep, here we have 1,000 entities all using some very nice sprite sheet animation. Let's look at the stats, and here we are, 1,000 entities running in the CPU in 6 milliseconds with 150-180 FPS. Now let's increase it up to 10,000. And right here at 10,000 we can already see some performance issues. So let's see how we can improve them. Here in our renderer we can easily improve a bunch of things. First of all, let's create the material property block outside and then simply reuse it. That will save a lot of garbage calls. And the same thing for our UV vector. So here we are reusing our UV array. And let's see how much we've improved. So here we are, and we got quite a nice improvement. We went down from 50 milliseconds per frame down to 30 milliseconds per frame. So right now we have 10,000 units, all of them being independently animated, and everything is running at 30 frames per second. So this right here is the simple way to do sprite sheet animation and render it. There is a way that we can further improve upon this and get even better performance. Here in the code, the main bottleneck is right here on the draw mesh call. Essentially, we're running through this function for each entity, so we're doing this call as many entities as we have. So if we have 10,000, we have 10,000 calls. However, on the graphics API, we have another function, and that is the draw mesh instance. This one allows us to render multiple meshes in a single function call, so we can greatly improve performance. However, that also contains a lot of tricky limitations and weird things we must do with it. So we're going to cover that in the next video. So right here we have built a nice simple sprite sheet animation system. We have in here a component that handles all the data that the sprite sheet requires. Then we have a system which works on that data in order to update the current frame and also calculate the matrix and the UV required to render it. This job is fully multi-threaded and using bursts, so it's insanely fast. And then we have our renderer, which takes all that data and does a simple draw mesh call. And here on the archetype, you can see that the only thing we need for this whole system to work is just the translation and the data component. So again, this is a very simple way of doing a simple sprite sheet animation whilst using pure Unity ECS. Stay tuned for the next video where we're going to explore the draw mesh instance and see how much better we can push this performance. As always, you can download the project files and utilities from unitycodemonkey.com. If you liked the video, subscribe to the channel for more Unity tutorials. Post any questions you have in the comments and I'll do my best to answer them. Alright, see you next time.